Number one, which of the following is a pure substance? Well, a pure substance is going to be something that doesn't have anything else in it, hence the purity. So concrete is a mixture of things. Nitrogen is a single element. That is a pure substance. Air is a mixture of different substances, and blue cheese salad dressing, also a mixture. Number two, passing an electric current through a certain substance produces oxygen and sulfur. This substance cannot be an element because an element, well, oxygen is an element and sulfur is an element, but if we decompose something, if we break it into pieces, it can't be, an element isn't going to break into two other elements without a whole heap of energy, which we will talk about much, much later. So number three, pick the chemical change that occurs when a match is held over a piece of metal. Well, the metal getting hot is a physical change. Water condensing, also a physical change. You have water in one state versus water in another. Burning a match, however, is a chemical change. It cannot be observed without changing the composition. And smoke deflecting light, also that's physical. Which identification is incorrect for the elements listed? Well, Zn is zinc. It is not zirconium, so that is incorrect. C is carbon, S is sulfur, and Cd is cadmium. Number five, which of the following is the smallest mass? Well, this is kind of goofy because you have to know what everything relates to a similar unit, really. And if you look at everything as it is compared to grams, let's say, convert everything into grams, you'll find that the femtogram is the smallest mass identified here. Number six, which is not a state of matter. Well, a vacuum is not a state of matter. It is a state, it's just not of matter. So which of the following statements is false? Well, a theory provides explanations of observed natural phenomena. That is true. A hypothesis is a tentative explanation or prediction that can be tested. That is true. We make hypotheses in labs and then we go test them. A theory can be proved correct if sufficient experimental data is acquired. That part is false. Theories cannot be proven correct. They can only be disproven or they can be supported. Number eight, which of the following is a chemical process? Well, the crushing of stone, you still have stone, they're just smaller pieces. So that's a physical process. The tarnishing of silver, however, is a chemical process. You're taking your silver in its pure state and you're actually creating a silver sulfide compound. You're changing the chemical nature of what it is. But dissolving sugar, you still have sugar pieces. They're just surrounded by water. And the melting of lead, you still have lead. It's just in a different physical state. Number nine, which of the following is an intensive quantity? Well, the density of a substance is an intensive quantity. It doesn't matter how much of your substance you have, it's going to have the same density. Which number is incorrectly labeled for number 10? Well, it is milliliters is microliters. This is the incorrectly labeled conversion. Go through each of these conversions using dimensional analysis and you will see. And it just dawned on me that I can show you that with this gadget. So if we're going to convert, say, our 5.8 times 10 to the negative 9 seconds into nanoseconds, you need to know what the equivalency expression is. So the equivalency expression is, well, how many nanoseconds are in a second? Okay, that's what I mean when I say equivalency expression. We can use what is called dimensional analysis. So 1 second is equal to 10 to the 9th nanoseconds. So that's my equivalency. If I put seconds here on the bottom and 10 to the 9th nanoseconds in the top of this little like fraction thing, this is called dimensional analysis. Sometimes this is called building fences because it starts to look like fence posts. But the seconds will cancel out. And then all we're left to do is the arithmetic. So I have 5.8 times 10 to the negative 9. And I'm going to multiply that by 1 times 10 to the 9th. And what I get is 5.8. So that is correct. 5.8 times 10 to the negative 9 seconds is 5.8 nanoseconds. So now let's do meters to picometers. I start with 2.3 times 10 to the negative 12 meters, and I need to use the equivalency expression. Well, 1 meter is 10 to the 12th picometers. So I do that arithmetic, 2.3 times 10 to the negative 12 times 1 times 10 to the 12th, and I get 2.3. So 2.3 times 10 to the negative 12 meters is 2.3 picometers. That is correct. Now I'm going to do the grams to kilograms because I've already told you that it's the milliliter one, but I forgot that I should be showing, so I'm going to be showing. So the 4.8 times 10 to the third grams, we need to use our equivalency expression. There are 1,000 grams in 1 kilogram. So in order to do this arithmetic, I take my 4.8 times 10 to the third, and I'm going to divide that by 1,000. So 4.8 times 10 to the third grams is 4.8 kilograms. So how many microliters is 4.8 times 10 to the negative 6 milliliters? Well, to set it up, we would put 4.8 times 10 to the negative 6 milliliters, and you need to know that there are 1,000 microliters in 1 milliliter. So 1 ml is 1,000 microliters. So that arithmetic is 4.8 times 10 to the negative 6 times 1,000. So 4.8 times 10 to the negative 6 milliliters is 0.0048 microliters. That's why question 10 is labeled incorrectly. So number 11, which of the following properties below is listed, is an extensive physical property? That would be the length edge of an average sugar crystal being less than 1 milliliter or millimeter. So an extensive physical property depends on the amount of matter, and the physical is something that describes its exterior, or something not necessarily qualitative, but something that can be seen or measured. So a 10-gram sample having a density of 1.58 grams, that is intensive. It doesn't matter how much of your sample you have. The density is going to be the density. The fact that you can be broken down into carbon, hydrogen, and oxygen, that's a chemical property, not a physical property. Sugar is a white solid. Again, it doesn't matter how much sugar you have. If you have white sugar, it's going to be a white solid. And the melting point is a physical property, but it doesn't matter how much sugar you have. The average edge length, though, does matter how much sugar you have. A small sample may or may not have an average crystal length of 1 millimeter. So number 12, which of the following common objects weighs closest to a gram? That is a shirt button. I believe that's given as an example in the e-text. Which of the following has been most extensively tested? Well, that would be a law. A hypothesis comes first, and we test that hypothesis, and after it's been tested ad nauseum, it becomes a theory. And then theories, when they are consistently supported and not refuted, they can eventually become a law. So that is the most extensively tested verbal statement to summarize some sort of a broad variety of observations and experiences. Number 14, which of the following is a physical process? The condensation of water vapor is a physical process. You go from gaseous water to liquid water. The baking of a potato, that is a chemical process. That's actually changing some of the chemical characteristics of the compound. An explosion is always going to be a chemical process. Rusting of iron is a chemical process. You're going from solid iron into an iron oxide compound. And the formation of polyethylene from ethylene, that's also a chemical process, the formation of a polymer. Number 15, which of the following is an extensive property? Well, so we're looking for something that's dependent on the size of the sample here, and that's going to be the mass. Density, boiling point, and freezing point, those all do not, it doesn't matter how much of the substance you have. Those should be consistent. So the symbol for the element of potassium is K. That is a common problem for a number of students who haven't seen chemistry either for a very long time or this is your first course in chemistry. The element potassium is identified by the chemical symbol K. Number 17, which prefix would replace the power of 10 in this scientific notation for meters? 3.68 times 10 to the negative 3 meters. That would be milli. Milli is times 10 to the negative 3. Number 18, the high temperature during a summer day was observed to be 92 degrees Fahrenheit. What's this temperature in Celsius? Well, let's work it out. So there are a number of different ways to represent the conversion from Celsius to Fahrenheit and Fahrenheit to Celsius. And it doesn't matter to me which one you use as long as you consistently get good results. That means you have an accurate method. So let's convert. I'm going to substitute 92 in for TF. So my TC is going to be 92 minus 32 divided by 1.8. So 92 minus 32, that means I have 60, and I'm going to divide that by 1.8. So that should be my temperature in Celsius. So 33.333, we could call that just 33. Number 19. Which of the following is a homogeneous mixture? That means it's going to be a mixture of stuff where you can't see the different pieces. Remember, a heterogeneous mixture, my favorite heterogeneous mixture is chocolate chip cookie. So a homogeneous mixture is one where you can't see the different pieces, or they're not going to settle out. So with muddy water, the mud will eventually settle to the bottom and the water will eventually float on top. So that is not homogeneous, that is heterogeneous. With dirt, you can usually see the different pieces. Like if you have rocks in your dirt, then it's heterogeneous. Iron filings in sand, you can see the iron versus the sand particles. Therefore, that's heterogeneous. Fog is also a heterogeneous, well, it's more of a suspension than a mixture. But gasoline is a homogeneous mixture. It's several different petroleum compounds, and you can't see one from the other. And it takes some work in order to get those pieces to fractionate, to differentiate. Number 20, which of the following does not represent a physical property? Well, color is definitely a physical property. It's something we can just see, at least most of us, unless you're colorblind. Sugar dissolving in water is a physical property. That is not a chemical property. Those pieces of sugar can then be pulled out of solution. Therefore, that's a physical property. Density is also physical. Boiling point is physical, going from one state to another. But reaction with oxygen is a chemical property. That's something that usually initiates flame of some sort. Therefore, that is a chemical property. Number 21, which of the following processes does not represent a physical change? So we're looking for something that's chemical. Any explosion is going to be chemical. So air to that when you're looking for a chemical change. Explosion or fire is chemical. Number 22, how many micrograms are in 0.0134 grams? Well, you have to know the equivalency, and 1 gram is 1,000,000 micrograms. So I need gram on the bottom and then 1,000,000 micrograms on the top. Then when I do this arithmetic, this is 0.0134 times 1 times 10 to the 6th. So I get 13,400 micrograms. So that should be the answer. Ooh, but we need scientific notation. So that's going to be 1.34 times 10 to the 4. Just a quick recap here. So 13,400 in scientific notation. Scientific notation means we need to have our coefficient part be more than 1 but less than 10. So I'm going to put my decimal right here. I'm going to change my color, so I'm going to put my decimal right here. So how many times do I move the decimal over in order to get to my original value? Well, I'm going to count. I'm going to jump. 1, 2, 3, 4. That means this will be 1.34 times 10 to the 4th. And that's how I convert from standard notation into scientific notation. Number 23. Which of the following is an extensive property? Well, we have boiling point, surface area, hardness, density, and temperature. The only one of these that is dependent on how much stuff you have is the surface area. Number 24, which of the following statements can be used to describe the study of chemistry? Chemistry is a chemical theory that is developed by testing a hypothesis that attempts to explain a set of observations and experiments. I think that is a little awkward, but that is the true statement. Number 25. For the following measured numbers, the number of significant figures is indicated in parentheses. So which is correct? Which is incorrect, I beg your pardon. So 40.04, those zeros are called bound. They're captive. So that is 4 significant digits. That one is incorrect. The next one, 0.00142, 3 significant figures, that is correct. Only the non-zero digits are significant in that number. 2038 has 4 significant figures. That is correct. That 0 is bound or captive between 2 non-zero digits. Therefore, it is significant. 4 times 10 squared has 1 significant digit. That is correct. When using scientific notation, only the significant digits of the coefficient part identify how many significant digits there are. The exponent is not part of the significant figure figuring out. Significant figure figuring. 0.0130 has 3 significant figures. That is correct. The non-zero digits are significant, and then the 0 to the right of the non-zero digits is also significant in this case. So for number 25, it's 40.04. Number 26. The density of liquid bromine is 3.12 grams per milliliter. What is the mass of 0.25 liters of bromine? Well, we're going to use dimensional analysis here. So I'm going to start with my 0.250 liters of bromine, and I'm going to convert it to milliliters. And the reason I'm converting to milliliters is because my density is in milliliters. So 1 liter has 1,000 milliliters. So now my liters have canceled out. Now I'm going to use my density as a conversion factor. So 3.12 grams per 1 milliliter. That's how that's read. And the milliliters cancel out. So what I'm left with is grams, and that's what I'm looking for. What is the mass? Grams are a mass. So now I just need to go through the arithmetic here. This is a little awkward, but 0.25 times 1,000, so I'll start there. 0.25 times 1,000, I'm multiplying across the top, times the density, 3.12. Now, if I had any numbers other than 1 in the denominator, then I would divide by that product, but I don't. So 780. Now I'm going to look for my significant digits, and that is grams. I have 3 significant figures here, and I have 3 significant figures here. So it should be 780 grams, but we would show that either by putting this in scientific notation, 780 times 10 squared, 7.80 times 10 squared, or putting a decimal after it. This is a misnomer, but this is our answer. It should be 780 with a period after it. Number 27. So 7 yards cubed is how many meters cubed? This one can be tricky. Now, I can only remember what I remember, so I'm going to take you through what I remember, and we can adjust from there. If you can get right from yards cubed to meters cubed, knock yourself out, but I'm going to go the long way. So we have 7 yards cubed. I happen to know that 1 yard is 3 feet, and I need to cube those in order to get rid of the yards cubed. Now, I also know that 1 foot is 12 inches. Again, I need to cube those in order to get rid of my units. Because I have to take it all the way down to inches, because I know that 1 inch is 2.54 centimeters. That's the part I remember. Again, I only remember what I remember. But I have to cube those in order to get rid of the units. So I can take it down to centimeters cubed. Then I know there are 100 centimeters in 1 meter. And then I have to cube those. So it gets a little bit hairy. So what are we going to do here? Well, we'll take 7 and multiply it by 3 cubed. I don't have a cubed here. 3 cubed. And then multiply that by 12 cubed. And then multiply that by 2.54 cubed. and I get a value. Now I have to divide that by 100 cubed. And I get 5.35 meters cubed. Now let's go through the dimensional analysis briefly. I have yards cubed, and I need to convert those yards cubed because this is what I remember. Yards cubed to feet cubed. And then I'm going to convert my feet cubed to inches cubed. Then I'm going to convert my inches cubed to centimeters cubed. Then I'm going to take my centimeters cubed, convert that to meters cubed. So the answer should be 5.35. Number 28, which set of measurements on a 2.00 gram standard is the most precise? Remember that precision tells us how close together our measurements are. So for the first set here, that end with 0.10, 0.20, and 0.15, we have a difference, a span of 0.10. For the second set of measurements, I have a span of 0.03. For the third set of measurements, I have a span of 1 whole gram. And for the fourth set of measurements, my span is 0.15. So because this span, 2.00, 2.01, and 1.98, have a total span of 0.03, they are the most precise because they are the closest to one another. Let's convert each of these and we'll see which one is incorrect. So 0.00654 times 10 to the negative 6. Let's put this in standard form, and then we can convert back to standard exponential notation. So if I have 0.00654 times 10 to the negative 6, now that means I'm moving my decimal to the left 6 places. I need to jump this 6 places. So 1, 2, 3, 4, 5, 6. New decimal place, fill in with zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then here's my 6.54. So for the true standard exponential notation, we do start 6.54. That part is correct. But now let's count. So I had 6 here, 7, 8, 9. So this would be 6.54 times 10 to the negative 9. So this one is incorrect. But let's go through one or two of the others just for practice sake. So 0.324 times 10 to the 8. Well, I'm going to jump 8 places to the right. 1, 2, 3, 4, 5, 6, 7, 8. New decimal place. Fill in the wells with zeros. 1, 2, 3, 4, 5. So 3, 2, 4, and 5 zeros. So now let's put this in correct exponential or scientific notation. So this would be 3.24. That part is correct. And let's see how many places I jump my decimal. 1, 2, 3, 4, 5, 6, 7. So you see that is correct. So for number 29, it was the first one. We kind of lucked out on that. Number 30, which of the indicated number of significant figures is incorrect? The first one is correct. Only the non-zero digit is significant in this value. The second one is incorrect. In scientific notation, it's all the numbers in the coefficient are significant. So 4.0 is significant. So that is 2 significant digits. There are 2 significant digits because the non-zero digits are significant for this 0.012. 1.79 does have 3 sig figs, and 3,104, that 0 is captive between 2 non-zero digits. Therefore, that is all 4 of those digits are significant. Number 31, an object will sink in a liquid if the density of the object is greater than that of the liquid. If the mass of an object is 9.83 grams, what volume must it have in order for it to sink in liquid mercury with this density? So we're going to take our values and we're going to equate. So density is equal to mass divided by volume. The density we're given is 13.6 grams per centimeter cubed. The mass we're given is 9.83 grams. And what I'm going to do is solve for a volume that would make this equal. If it's equal, it's not necessarily going to sink. So I need a density. I need this density to be the minimum. So I'm gonna put my little alligator symbol, my caret symbol here, my less than symbol. And I'm going to solve for volume. So I multiply the word volume by both sides. I get 13.6 grams per centimeter cubed times, I'm going to use just volume, and that's going to be less than 9.83 grams. Just going to work out the algebra for you here. Now I divide both sides by 13.6 so that I get volume is equal to 9.83 grams divided by 13.6 grams per centimeter cubed, and then the units will end up being centimeters cubed. So I take my 9.83, divide it by 13.6, and I get a value of 0.72, I would round that up, 0.723. So my volume should be less than 0.723 centimeters cubed. That's that one. Number 32, 1 milligram per centimeter squared equals how many kilograms per meter squared? This is a giant dimensional analysis problem. So I have 1 milligram per 1 centimeter squared. I'm going to start by converting my milligrams into kilograms. I know there are 1,000 milligrams in 1 gram, and I know there are 1,000 grams in 1 kilogram. Okay, so my milligrams are now kilograms. Now, if I did this arithmetic just like this, I would have kilograms per centimeter cubed. I need meters cubed. I know there are 100 centimeters in 1 meter. Now, you could do it the way I did in the previous dimensional analysis problem, or you could go through and do it again. 1 meter. And that gets rid of the 2 centimeters, centimeter, and leaves me with meters squared. So to do this arithmetic, I multiply across the top. So 100 times 100. And that is my numerator. And then I divide it by the product of the denominator. Now, it is important that you use parentheses in a case like this, because your calculator will work with standard orders of operation. So if you don't use parentheses, it doesn't know. So 0.01 is the answer. And the units for that, let's see, we're left with kilograms per meter squared. But that's not what we're given here. We're given an exponential notation. So put this in scientific notation. This is 1 times 10 to the negative 2, because we're less than 1 and we're going over 2 jumps. So kilogram per meter squared, 10 to the minus 2. If an athlete runs a 10-second 100-yard dash, what is his or her speed in miles per hour if 1 mile is 1,760 yards? So we have another dimensional analysis problem. We have 10.00 seconds. Miles per hour is what we're looking for. So we're going to start with yards. 100.0 yards in the numerator in 10.00 seconds. We want to end up with miles per hour. I'm going to take those seconds first and convert them into hours. And I'm going to go the long way here. There are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. So my seconds have canceled, my minutes have canceled. I'm left with hours in the denominator. Now I have yards per hour. I want miles per hour. So I want 1 mile in the numerator. 1 mile is or equal to 1,760 yards. So my yards cancel out and I'm left with miles per hour when I perform this arithmetic. And the arithmetic is 100 times 60 times 60. And that is my numerator. And now my denominator is 10 times 1,760. So I get 1,227, which is way, way off. I don't know what I did there, but the answer is 20.45 miles per hour. Both of these numbers have 4 significant digits. This is a definition, so it doesn't go into the sig fig, so we need 4 significant digits in our answer. 20.45. Number 34, for a given temperature, how do the Fahrenheit and Celsius values compare? You have to remember your scales here. So Fahrenheit values are going to be higher than Celsius values above about -40, and they're going to be lower than Celsius below -40. It's weird, but it's true. Number 35, which is the volume of a bar of metal with the dimensions 2 meters by 20 decimeters by 20 centimeters? We need to get everything into the same unit. I'm going to choose meters. I don't know what the answer is supposed to be, but I do see we have centimeters, decimeters, and meters and decimeters. Test taking strategy, I would probably convert to decimeters because there are two answers with decimeters, but I'm going to convert to meters because they're kinder in my head. So we have 2.0 meters, 20 decimeters. A decimeter is 10 centimeters. So we have 20 decimeters, and then let's see, 1 decimeter is 10 centimeters, and there are 100 centimeters in 1 meter. So we have 2 meters then. So 2 meters times 2 meters times 20 centimeters is 0.20 meters. So 2 times 0.2, I get 0.8 meters cubed. Well, it would be 80 because, well, no, it wouldn't. These have one significant digit. So 0.8. But that isn't one of my answers. So now I need to convert. And I am going to convert to decimeters since 2 of my answers have decimeters there. So 0.8 meters cubed. There are 10 decimeters in 1 meter. If I cube that, so 0.8 times 10 cubed, I get 800 decimeters, and this is 800 decimeters. So that is the answer. Number 36, how many grams of alcohol with a density of 0.9 grams per centimeter cubed will have the same value as 20 grams of mercury with a density of 13.6 grams per centimeter cubed? So let's see, what is the volume of 20 grams of mercury? Let's start there. So 20 grams of mercury has a volume. Let's see, we're going to use the density as a conversion factor. So 13.6 stays with grams of mercury, and that is per 1 centimeter cubed. The question is how many grams of alcohol with this density will have the same volume. So then I'm going to use that density, 0.900 grams of alcohol, 1 centimeter cubed. Grams of mercury cancel with grams of mercury. Centimeters cubed cancel with centimeters cubed. And then I'm left with grams of alcohol, which is what I was hoping to leave with or end with. So 20 times 0.9 divided by 13.6, and I get 1.32. That would be grams of alcohol. Number 37, which of the following objects is the most dense? Well, let's find our density, and let's make sure that we're converting everything to the same units. So I've worked out all of the densities here. Which one is the most dense? I converted everything to grams per milliliter, and the most dense is then going to be the density with the greatest numerical value, and that's going to be D, or this one here, because it works out to 2.0 times 10 to the 22nd grams per milliliter. Number 38, if we're going to perform these operations and express the answer with the proper number of significant digits, we need to remember our order of operations. Now I'm going to have to zoom in on this one a bit. I think those are both plus signs. So because we are adding here, we're going to be limited to the tenths place. So we go through the calculation as normal. 28.1, go ahead and put it in your calculator, plus 0.53, plus 75.321, and I get a value of 103.951. But we will be governed to the tenths place because that is the number with the least precision. It goes to the tenths place. So we would round this to 104 0.0. Number 39, which of the following numbers is incorrectly rounded off to 3 significant figures? This is 3 significant figures. That is correct. This is 4 significant figures. So that is incorrect. And then these other 2 are 3 significant digits. So that is correct. Number 40, the distance from the Earth to the Moon is approximately 240,000 miles. If we have an airspeed, how many hours would it take ignoring gravity? So this is a dimensional analysis problem. I'm going to start with miles, 240,000 miles, and I need to convert that into kilometers. 1 mile is about 1.61 kilometers. So you need to aim for kilometers per hour. Now I can use that rate as an equivalency expression. So 2,400 kilometers take 1 hour. The question is, how many hours would it take? So now I perform that calculation. 240,000 times 1.61 divided by 2,400, I get 161 hours. Number 41, how many dozens of particles of dust are in 2.45 grams if each dust particle has this mass? So again, we're setting up the dimensional analysis. How many dozens of particles if each dust particle? So we have 2.45 grams. We want to end with dust particles. And what I know is that one dust particle has a mass of 2.51 times 10 to the negative 4 g for grams. So I'm going to divide 2.45 by 2.51. Use the exponent key in your calculator or put your number in parentheses. And I get 9,760 particles. Well, I should take that one step further, shouldn't I? So there are 12 particles in 1 dozen. So I need to take this number and divide it by 12. And I get 813 dozen particles. Zinc has a density of 446 pounds per cubic foot. What is the density of zinc in grams per cubic centimeter? So this is a dimensional analysis problem. So we have 446 pounds per cubic foot. 1 pound is 454 grams. So that will convert me. Now I have grams per cubic foot. Now I don't know a direct correlation between cubic feet and cubic centimeters. So I'm going to go with what I do know. I know that 1 foot is 12 inches. So in order to, remove the cubic feet, I need to cube this. I know that 1 inch is 2.54 centimeters, and I need to cube each of those as well. So now I'm going to perform the arithmetic. So I multiply across the top. So 446 times 454, and I get 202,484. But I'm going to divide that by the product of the denominator, which is going to be 12 cubed times 2.54 cubed. And I get 7.15. In the units here, just double check my units. I'm left with grams in the numerator and cubic centimeters in the denominator. So 7.15 is what I'm looking for. 7.14, close enough. Number 43, perform the indicated operations expressing the answer to the proper number of significant digits. So I have addition and I have subtraction. Go ahead and put this into your calculator. 13.236 plus 6.2 minus 5.28. I get 14.156. But the question specifically, we need to understand what the proper significant figures are. When adding and subtracting, you're bound by the number that has the least number of significant digits, the least precision. And here, the 6.2 only goes to the 10th place. That means my answer can only go to the 10th place. So 14.156 would round to 14.2 when you're looking at the 10th place. Number 44, a spherical ball with a diameter of 5 centimeters what is the mass in grams of the sphere if lead has a density of 11.34 grams per centimeter cubed? Well, with density, we need mass, we need volume. The mass, what is the mass is what we're looking for. So let's calculate the volume and use the density. The volume of a sphere is found by taking 4/3 pi r cubed. R, the radius, is half the diameter, so 2.5 centimeters cubed. So put it in your calculator. 2.5 cubed times 4 divided by 3 times pi. You can approximate pi at 3.14 if you wish. And the volume I get is 65.4 centimeters cubed. That's not the answer. That's just the volume. So now I'm going to use that volume, 65.4 centimeters cubed, and I'm going to use the density. The density is 11.34 grams per centimeter cubed. 65.4 times 11.34 divided by 1, of course. I get 741, and that would be grams. So that would be 7.4 times 10 squared grams with my 2 significant digits. So 7.4 times 10 squared. Number 45, which number of significant figures is incorrect? Well, negative 15.250 has 5 significant figures, so it's going to be this first one here, because this 0, this ending 0, is significant. In 10.0800, all of those zeros are significant, so that is 6 significant figures. 8.1441 has 5 non-zero digits and 5 significant digits, and 0.00050, that actually has 2 significant digits. So we have 2 answers here for number 45. But the system wants this one at the bottom, 0.00050. That is 2 significant digits. Number 46, if there are 6, I think that's supposed to be, no, it's not eggs. 6 eggs per OG and 3 OGs per ID. How many eggs are in 4 IDs? I'll be honest, this one had me swearing off camera. So if we have 6 eggs equals 1 OG, and 3 OGs equals 1 ID, how many eggs are in 4 IDs? Well, we're going to start with 4 IDs, and then we'll use our conversion factors here. So 1 ID is 3 OG, and 1 OG is 6 IG. So I multiply across. 4 times 3 is 12. 12 times 6 is 72. So the average distance from the Earth to the Moon can also be expressed as a scientific notation value. Meters, let's see, that would be 3678. So 3.83 times 10 to the 8th meters. So that's not the answer. But it would be 3.83 times 10 to the 10th centimeters. That would be correct. And finally, our last problem. A student performs an experiment to determine the freezing point of water. 3 values are obtained. The thermometer has a mark for each degree. Which of the following statements are true? These values are precise, but they are not accurate. And that's because the values are close to one another, even though they are not at 0, which is what we would expect.